So let us start. Just a second. Okay, fine, let's start. So last time we saw what is a QCQP? Yes. 1 second, let me fix this. Okay. Yeah, so we saw what is a QCQP, right? So that is like a quadratic program, an extended version, or a more generalized version where we have a quadratic term in constraints also, right? So we saw that what is the feasible region in that case. Now let's move to more generalized version. Second order con programming. So now the thing is, so now what we are seeing is a more generalized version. So like this, right? A more general class of our optimization problem, which contain all these subclasses. So second order con programming has this shape or the form. You have a function to minimize, which is a linear function, affine function, and the constraints are given by the second order con. And of course, you have a linear constraint given by an affine function. This is same as the previous case, but the new thing here is it should have a second order con constraint. So what does this mean? So if you remember from our discussions on convex set, we studied about norm cons, right? So what is a second order con, which is also known as Euclidean norm con. So norm cons generally have a form like this, but if you use a second order norm, it is a second order norm. So second order norm con or Euclidean norm con. So it has a shape like this, like the ice cream cone, right? Something like that. So where you have x here and t here, so it's a pair xt such that norm of x has to be less than or equal to t, but t is a non-negative quantity. So this is second order cone. So now what we are saying is, so this constraint is something similar to this constraint right here. So this is a second order constraint. So in other words, you can say that this pair x plus bi. So here we can say that xt belongs to this second order cone. Okay, or I will denote this as second order cone associate xt. The pair xt belongs to second order cone. So the thing is, what is the what is the dimension of this cone variable? X has a dimension if you take Rn, right? And t is a scalar, so it has a dimension 1, right? So total dimension will be this is in R, t is in R, so total dimension will be Rn plus 1, right? So here, so what we have is from this constraint, that means the first guy ax plus b plus that one and this cx plus d, that should belongs to a second order cone. Okay, so here the dimension of the first quantity is Rni. Okay, because we have the matrix is having dimension ni cross n. Okay, so when you multiply vector x with matrix, you will get another vector having dimension ni. So this guy, the first part of this pair is a vector with with dimension ni, and second one is in R. That's a scalar R1. So what we are saying is minimize this affine function where the constraints is this your x uh, means x plus b plus c transpose x plus d has to be in a second order cone. So here, yeah, yeah. So here you can see that how do you say that this fits into, for example, a QCQP or LP is a second order cone program. For example, for instance, here if you just make this a to be 0, what happens? Then it's like a constant. BA is a constant, right? Is less than or equal to C transpose X plus DA. That means it's a LP, right? So only term in that case, if A is 0, only term involving X is this part, this C transpose X, which is a part of an affine function, right? So then in that case, it's an LP. So when A equal to 0, this is LP. Okay. Yeah. So yeah, one thing is here we were saying just one inequality, but it can have several inequality, like for I equal to 1 to m. So in total, there are m second order conditions here. Okay. AI, A1, A2, A3, A1, A2, A3, like that. Okay. So yeah, so it's like saying we have several second order cone and we're considering intersection of all. And yeah, so one way to visualize is a equal to 0. Other way is make this AI as a what? It's a vector. Means it's a number of rows equal to 1. In that case, what will happen? So what I'm saying is this is a vector. So AI, let that be 1 cross n AI. Okay. In that case, this will be a vector. This will be a vector, right? See what's so then what is AIX? So AI is 1 cross n is n cross 1. Okay, so sorry, it's not a vector. Now this will be a scalar. So you are multiplying 1 cross n with n cross 1, right? Yeah, so that will be a scalar. So then what is this meaning? It will be like you have a scalar and you are taking the norm of that Euclidean norm. So in that case, it will be simply AIX, the absolute value, because it has only one dimension. It is like root of x square, right? So you have an absolute value here and a scalar term here. So that's again, you can express as a linear constraint, right? So when you say something like x is less than or equal to 2, you can rewrite this as minus 2 x, right? So you can bring two inequalities to represent this. So when ni equal to 1, again this can be visualized as a LP. Now what? Now let's see how this can be represented as a QCQP, or how QCQP fits into this framework of SOCP. So yeah, one obvious way to see this is, for example, here, let's just take Ci to be 0. Then see how that is a QCQP. So when Ci to be 0, then what you have is just this guy here. Hi. Then what we have is this guy here. That is the norm 2 of ax plus bi is less than or equal to, this is 0 now, just di. Okay. Square both sides. Fine. So you square both sides. Then here you will have AI, something like AI transpose AIX plus BA transpose AI plus AX plus BA. Okay, so that will be a quadratic term, right? So what I'm saying is just when c equal to 0, this term will not be here. If you square both sides, you will get a quadratic constraint here. So then that's a QCQP, right? What is QCQP? It's a quadratic programming, generalized version of quadratic programming where you have a quadratic constraint, right? So then, sorry? It's program. Quadratic programming, QP, QCQP, quadratic constraint, quadratic programming. Okay. Yeah. So that's it. But one thing you may ask is for QCQP, you also have a quadratic objective function, but here you have only an affine function or linear function here. So then I just said this can be if ci equal to 0, then this is a QCQP. But what happens if you have something like here also a quadratic term, here also quadratic term, then how can you see that as a SOCP? That's the question, right? So then maybe there are many ways to do that. I will not go to that, but you can read this later, where they are showing a quadratically constrained quadratic program. How can they express in the form of a second order con program? Yeah. So so the conclusion is that SOCP is the general class of all these guys, QCQP, QP, LP. Okay, any of these classes, subclasses will fit into SOCP. Yes. Yeah. Now let's move robust linear programming. So far we were talking about optimization problem where these coefficients C, A, B, whatever it is, they were deterministic. There is no randomness associated with that. For example, here this is a robust LP where you are minimizing a linear function, linear constant, right? Linear inequality. But what about C, A, and B? They are constant. That's how we treated them, right? We didn't say that it's a random variable or we don't know A for sure, right? We know, we said that they are constant. We know them, okay? But now we will see what happens if they are random variable. They are not a constant or deterministic. They are coming from a stochastic model. So yes, let's see. So here we will discuss just for the case of A. So we say that AIs are not constant. They are we don't know about them like as a constant. They are like a random variable. That's what we are going to see. So one thing is, yeah. So this is what. So there are many ways to treat such randomness. So one thing what we do is we just go for a deterministic model where we say that, okay, I do the same problem, but since AI, what is AI? AI is a vector, right? AI is a vector, right? So now what I say that I'm not very sure about AI, but I'm sure that what information I can provide about AI is that AI is inside an ellipse. So now I know that my AI is somewhere inside here. So it can be here, or it can be like this, like this, like this, something like this. Okay. So it's like, yeah, it's inside an ellipse. Okay. Now what I do is I just replace this. I write the same optimization problem, but say that AI is inside this ellipse. AI is not constant here. Okay. This is one way to do this. Fine. So we'll see how to proceed from here. That we'll see soon. So what I'm saying is that this can be treated in two ways. One is deterministic model, where we assume this inside analysis. But here we are not we are not taking into account of any probability distribution or randomness of AI. We are just saying that it is inside an ellipse, so it can be anywhere here. But other thing is a stochastic model, right, where we bring probability. So how do we say that? How do you form a stochastic constraint here? So the thing is, in contrast to the models that we discussed here, the problems that we discussed here, the constraints must hold with a chance. Okay, so what I'm saying is, okay, my A transpose X less than or B is my constraint, but it holds with a probability, for example, 0.9. Okay, so this is the way we are stating that, okay, this is the constraints are satisfying, but I'm not 100% sure about that. It is satisfying with a probability. So how do you write that? So probability of this is our constraint, A transpose X less than B, right? Probability of that means probability that this constraint is satisfied, that is greater than theta. So this is a probability. So if I say that it had to be half, okay, that means 50% of case this is going to be violated. That's the key. So this is called chance constraint in optimization, where you have a constraint and that is satisfied with a probability. In that case, that those sort of constraints are called chance constraint, and there are many theories developed to deal with such constraint, but we won't go into detail, but we'll just see some of the aspects here. So now, yeah, why we are seeing this is a linear programming. If there is a randomness, so this is the linear programming, and if there is a randomness associated with the coefficients, okay, for example, here we are considering AI. So when there is a randomness associated with the AI, this coefficient, then we can rewrite the linear programming using an SOCP. Okay, then you cannot write a linear programming by accounting this randomness. That's very difficult. That's not possible. Then what we do is we rewrite the problem by including this randomness and come up with an SOCP. So that's what we are studying here. We just, so what is SOCP? Now we are seeing how a linear programming with a chance constraint can be rewritten to an SOCP framework. So first, so we saw two approach. One is deterministic and one is stochastic. So let's see deterministic approach. How can we write in the form of an SOCP? Yeah, so let's choose an ellipsoid. So what was that? A deterministic approach. We just write the LP and say that AI belongs to a particular ellipsoid. This is our uncertainty region. Okay, so let's consider an ellipsoid here. Epsilon I equal to AI plus PIU. So we saw in while we discussing convex set, an ellipse can be represented in this form, where AI bar, this is AI bar, is sort of the center of the ellipsoid. It is the center of the ellipsoid, and we have the ellipse, and what will be the this axis length, that will be determined by the eigenvalues of this matrix PA. So this is how we represent a matrix in a vector form. Okay, so AI, this is the mean plus the matrix into U, where the norm U or length of U has to be less than or equal to 1. Yes, so what happens now? Yes, yeah, so this is determined by singular values and singular vectors. So this direction will be given by the singular vectors, and the length will be given by singular values. Yeah, so let's see how can we write this. So what we have is a robust LP where we are saying that C transpose X and this constraint and AI is belonging to an ellipsoid, right? So now we are trying to, so since this term is difficult to handle, we are trying to rewrite this using an SOCP framework. So what I do here is, yeah, I have the same objective function here, but this together I will rewrite. So yeah, how can we do that? So so we have from robust LP, this constraint has to be satisfied, A transpose X plus B. Now what I do is, instead of A, I bring this uncertainty. Instead of A, I pick the vectors from the ellipsoid, that is these vectors, and I plug it here. Okay, instead of A, I am plugging it here. And now what I'm saying is, what I do is, I will take the maximum value of that, supremum of that. And then I will say that that supremum should be less than or equal to Bi. Okay, that means I will, instead of A, I am replying a vector from the ellipsoid, and then I will take maximum of that, and then I will say that that is less than or equal to B. Then, so if that is satisfied, here we are taking the maximum, supremum, maximum of that, right? So if maximum is satisfied, that is falling within the ellipsoid, then it will be satisfied for all other values of U, right? So see here, how do you define an ellipsoid? Center plus a matrix into a vector U. Okay, so when you vary U, U has a direction and a magnitude. So when you vary U, you can get different vectors for different points in the ellipsoid, right? So what I'm saying is, I will reprice uh, A with the points from the matrix, and then I will find the maximum or supremum of that. So when you find supremum of this guy, so first term is a transpose X. So remember, not there is a bar here, which means that is the center. We assume that we know the center. Okay. So this will not affect, supremum operation will not affect the first term because there is not U. Only the variable here is U for the ellipsoid. Okay, we fix the center and we fix the directions. We know P matrix. So the variable is P. So this term we can take outside. And now the supremum is applied to this part, which is written like this. And we already saw in last class, here we have a vector U, and you are taking inner product with another vector P transpose X. In that case, the maximum value will be the norm of this guy, because this is like this inner product is norm of this vector into norm of this vector plus an angle between them. So this will be maximum when, and you can take maximum value, a maximum value of 1. Okay, so this will be maximum when you take the maximum magnitude and the angle, cos of the angle will be 1. So that means it will be just this norm. This we already saw in one example from last class. You can see that. So now what I see that the maximum variation is this. Okay, so now just I replace the constraint with the maximum variation and say that that is less than or equal to B. So if this is satisfied, then it will be satisfied for all other U's, right? So this is it. So now what we saw that we have an LP where there is an uncertainty. We don't know AI for sure, right? So that we rewrote like this. Now it's an SOCP framework. So this is one way to do this. That is our deterministic approach. Now we'll see what is stochastic approach in this case. So let's see now in the stochastic approach, we will bring probability. Okay, so let's assume that AI is a Gaussian with mean AI, So now AI is a random variable with a Gaussian distribution, and it has mean a bar, okay, and covariant sigma. So you can write this, right? So AI is distributed under a Gaussian distribution with mean and covariance. And now let's see. So how do you get now what we want to do is to find this probability. Yeah. So this is the stochastic approach where we introduce this chance constraint where we say that the probability that the constraints are satisfied is greater than a value of theta, a value of theta. So now we have to find what is this guy. So since we assume Gaussian distribution, so you know that, right? For Gaussian distribution, for example, yeah. So what I do is I make it zero mean, the random variable to be zero mean and unit variance. I just normalizing, shifting to mean as to zero mean and normalizing. So a probability under a Gaussian distribution. So this is the random variable. I am shifting by mean u bar and dividing that with the standard deviation. So then this will have unit variance and zero mean. So how do you find this probability? So same thing I will do for on the right side also, the values. Okay. So there also so see what I have to, what we want is like here, we have to find the probability of this guy. Okay. So my u is a transpose x. Yeah. So if you have this means if you have a probability like this where u is a Gaussian distributed random variable and mu sorry, this is mu. Okay, this is supposed to be mu. Mu bar is its mean and sigma is its standard deviation. Then now we can find the probability using this q function or something you have learned. This is not q function, that will be 1 minus of this. So this means you have a PDF. This is a PDF of zero mean and unit variance. Okay, in that case, or that's called phi of phi here, which is, this is a PDF. So phi is the cumulative distribution, CDF, cumulative distribution function. So phi is given by integrating this guy. So what is this guy? This is a Gaussian function with zero mean and unit variance. Okay, so integrating that from minus infinity somewhere here up to the point where you want to calculate the probability. This you already know from your bachelor's, right? So for example, if I do is uh, normalize my random variable. So here u is, so A has a mean AI covariance of sigma I. Then A transpose X will have a mean. So this is like A into a constant, right? A is the random variable here, and into X, a constant, A transpose. So that will have a mean A bar transpose X, okay? And various X transpose sigma I into X. This we already proved in the last class, we can see, or it's very easy to prove. Just use the basic formula for the variance or covariance. Yeah, you will get this. So now since now you have to shift the mean by this amount, this is the mean, right? And the standard deviation corresponding to this guy. So now my mean is this, and the standard deviation or variance will be, variance of this air transpose X will be this, and I can write that in this form: sigma root of sigma into root of sigma inside here. Then I do some rearrangement and I get this variance here. Okay. So this is the variance. Remember, this, our original vector a was a vector, right? A random variable. That was a vector, random vector. Now when you multiply that with another vector, take an inner product with another vector, that's a scalar. Okay. So sigma square is the is the variance associated with this scalar. So this will be a scalar. Yeah. So only thing is these are just you can just to derive and see. So these are shifted mean and normalized with the variance. Okay. So now this probability I can write like this, where phi is the CDF associated with a unit variance and zero mean Gaussian distribution. Now, how do you write the SOCP associated with this problem? So this was our original problem where we say that this constraint is satisfied with the probability. Now, what I do is I just since so the probability is greater than eta. This means phi of this guy greater than or equal to eta, right? I just rearrange, take the phi to right side, phi inverse, rearrange this, then you can write in this way. A transpose x plus phi inverse n into the variance is less than or equal to ba. So plug that here. So you can write this. Is it an SOCP? Just see there is some problem with this. This will be an SOCP when see how was our definition of SOCP? Yeah, so here this term has to be positive. So here this will be an SOCP when where are we here? Yeah, when the term involving norm is positive. That means here everything is positive here in this term. Apart, we don't know about phi inverse n, right? So at what time phi inverse n will be positive? In which case phi inverse n will be positive? So it's not n, sorry, it's eta. Okay. So at which case, my question is, for what value of eta, phi inverse eta will be positive? Eta is a probability, right? So so see what is probability here? It's an area up to the point where we up to the point where we want to find the probability, right? So what happens when y is negative here? So the probability will be less than half. So if you take all area under this period, it will be 1. Probability will be 1, right? So if you take half of this, probability will be half, right? So when the value of y is less than 0, okay, then the probability will be eta will be less than half.
No, but the probability can't be limited, right? It will be always
I didn't say probability is negative. I say when the value of y is less than 0, then probability is less than half. That's what I say. The area, yeah, area will be, for example, when y is here, the area will be this. That will be less than half. Okay, that means when the probability is less than half, this term will be negative. So this will be SOCP only when you have a probability towards this side. Okay, so we are calculating the probability. Okay, these are not big things, you can read later. So just maybe you have to revise a little bit about your probability theory. Yeah. So only thing is, yeah, so we wrote this is easy, but only the point is this term has to be positive. For that the probability has to be greater than half. But is it a reasonable assumption that see in any problem we want We don't want to say that, okay, my chance that my constraints are satisfied is less than half. So then that's not a good problem, right? So I'm saying that I have optimization problem, and the chance that my constraints are satisfied is 25%. Then what does that mean? Just 25%. Then that doesn't make much sense. So always we want the chance to be like 90% or 99%, something like that. So in useful particle application, this you can when your probability is high, this will be readily an SOCP. Okay. Yeah, so that's it. So we saw two approaches. So what we are seeing here is, again, we were learning SOCP. Then we saw that an LP where there is a randomness associated with the coefficients can be now dealt using the framework of an SOCP. So we saw two approaches. One is using the ellipsoid, a deterministic approach, and again, second one is using a random variable. Means we bring a probability and then we wrote. In both approach, we wrote or we rewrite the form optimization problem using an SOCP framework. That's what we saw. Yeah, so let's move. So I will I will skip to a new topic, but we will come back to this later, okay? Because now we are here. Now we are here. We just learn SOCP. Now I want to move to a higher class of this, okay? In the order, in the hierarchical order. I want to move to higher class. So GP will not fit into the next one, GP. Geometric program will not fit into that hierarchy. So I am just skipping this now, but we will come back to this slide later. Yeah, so let's move to another next class. So which is a conformal problem. Okay. So before that, let's just generalize the optimization framework that we saw so far. So now what I'm saying that, okay, I have a same framework, minimize F0x with respect to some inequality constraint and an equality constraint. Okay. But only thing now, only difference is that this inequality is now defined using a generalized inequality. Okay, so you can say that you can see this here. This is defined with respect to a how do you define a generalized inequality? In association with a cone, right? That, see, we saw. So this is why you have to revise or learn each day, otherwise it will be difficult again. So we will be finishing this by Wednesday, right? So only if you know the concepts very well, then only you can survive in duality and the remaining topics. Okay, so all these concepts will be very often used. So so what I'm saying is you are defining an inequality. So this, we already saw some of this. So in real case, real variable case, for example, in R, so you can say that 2 is less than or equal to 3. But what happens in Rn? You have a vector. This is 2. Okay, you have a vector. So how do you say vector x is less than or equal to vector y? So this can be said only using a generalized inequality. Okay, so here we use R plus. So this means a component-wise inequality. We saw this in detail while previously, right? So this is a component-wise inequality. Now in in metric space, how do you say? So now we have, this is for vector. For matrix, we say matrix X is less than or equal to matrix Y with respect to the, so here the cone was R n plus. Now for matrix, the cone will be cone of positive semi-definite matrix Sn plus. Okay, so these two are most often used inequality. That means when you compare two vector, you are using the cone Rn plus positive or non-negative of that.
Mm.
Then that will lead to a component-wise inequality. When you can say x is greater than y, when each component of x is greater than each component of y. For matrix, you say matrix y is greater than matrix x when y minus x is positive semi-definite. Because there we are using uh, the cone that you are using there is a positive semi-definite cone. So these are the most often used form of inequality, but you can come up with any cone, not any cone. We saw that the cone has to be proper cone to be associated with a generalized inequality, right? So if you have any proper cone, you can define there can be a generalized inequality associated with that. But often we use these two guys. Yeah. So now what I'm saying is our original or standard optimization framework, a convex optimization framework, now can be more generalized using by replacing this inequality uh, to a with replacing this with a generalized inequality. So now what I'm saying is fi is less than 0 with respect to the proper cone ki. That's what I'm saying. So yeah, so everything is same. F0 is convex. Fi, yeah, fi is a function uh, with respect and the inequality is represented now using ki. Now the thing is fi is not from Rn to R. Earlier we were having something like this. Now it is from Rn to R, then fi. So far we were saying that fi has to be convex. Now fi has to be k convex. What is k convex? It's same as our something very similar to we already saw this. So this was our Jensen inequality, right? Mm, theta into f of x. That's 1 minus theta into f of y. So this is, we say that this is when f is convex, right? In this case, f is convex. But for k convex, now f maps a vector to another vector. In that case, we have to use the generalized inequality and bring a cone to introduce that generalized inequality. Now we say that the function f is not convex, it is k convex. So you can define the convexity of this special particular function only using a cone, a proper cone. Okay. So what I'm saying is now the general framework has, so this is the place where we brought change. So one is fi has to be k convex, and the other thing is this inequality is defined with respect to a cone, a proper cone. So this is called a convex problem with generalized inequality constraint. Fine. Now, so this is also this can also be solved easily as a convex problem. It is a convex problem actually. Everything is convex. So the same property like whatever we saw, local minima is a global minima, all these properties, convex, the feasible set are convex. Everything will be satisfied here. So this is a generalized inequality constraint. Now what we are saying is a special class of these, which is very important for us. Okay, which is called conic form of problem. So what is a conic program? Conic problem. It is this guy when this f0 and fi are affine. Okay. So just rewrite this. Okay. Now what I'm doing is instead of f0, I'm using an affine function here. Again here an affine function here. Okay. So now what you can say about this? So based on this is called conic form of problem. and this will be the like outer generalized class of all the problems that we saw so far. We will see how can we prove this. Okay, we will see that. So just see this. So this extends the linear programming. So my question is, let's try to understand this. So they are saying linear programming is when the cone is R plus, Rm plus. Why? So just I'm considering this part where it says linear programming is this framework when you consider the cone to be Rm plus, no negative of that. It's an affine function, but we are talking about this cone, right? Why? No, no. My question is, so this looks like a linear program, right? So this is an affine, this is an affine function, but this is not linear programming always, because there is a guy here. You have to be careful that. Okay. So here, let's see. Let's take f to be a matrix. X is a vector. So when you multiply f with x, what you will get? You will get a vector. Okay. Vector plus vector. So let's call this guy as y. So what you are saying is y is less than or equal to 0 with respect to a cone k. Okay. So in which case this will be a linear program when the cone is r plus, rm plus. Because in that case, what will be that? It will be component wise, element wise comparison. In that case, what you are saying is, uh, what you are doing is, so for example, yeah, here, what you are saying, when k equal to rm plus, what you are saying is instead y1 is less than or equal to 0, y2 is less than or equal to 0, like that you are saying. Each component is satisfying this inequality. In that case, what's happening here is this will be like a bunch of vector inequalities. Fx plus g, the first component is less than or equal to 0. Similarly, uh, yeah, for all I. So this is like ax plus b less than or equal to a1x plus b, b1 less than or equal to 0, a2x plus b2 less than or equal to 0. You have many linear inequalities. Yeah. No, you are saying you have an affine function, for example, ax plus b is less than 0. So then what is x here? Our optimization variable, right? So x can be anything, right? I'm yeah. Yeah, yes. Real cone. Yeah, so what I'm saying is, no, you are confused with that. So it's not about defining the domain or something. It's how do you define the inequality. So what I'm saying is, so I got what you're saying. I think you're, so let's say I'm comparing two vectors with respect to this cone r plus. With respect to this cone, okay, r plus. So this will be r2 plus. Okay, so the vector that I'm comparing need not be in this. Okay, the thing is, for comparison I am using a cone that is r plus. Vector can be anything. Vector can be this guy here. So I am comparing these two vectors, x1 here, x2 here, and I'm saying whether x1 is greater than or x2 with respect to this cone. Okay, so vector need not be in that. Okay, so when I make this statement, this is this k is for defining this inequality. Okay, that has nothing to do with uh, the domain or something of x. Okay, so x can be outside r plus. Okay. Yeah, what we were discussing is when this cone is r plus m, so this will be a component wise inequality. In that case, we are what we are saying is it's like just take the first. So you have a, maybe I will write it here somewhere. You have a vector here. Into what was that? X, yeah. So x is this. Okay. So it was, this has to be less than or equal to 0. This was the original condition. Now what I'm saying is when k equal to r plus m, rm plus, so what will be, this will be component wise inequality. That means this, the, for example, I will write the first row of this, that will be f11, f12, f13 into x1, x2, x3 will be less than or equal to 0. Now this is an normal inequality for scalars. Okay, so like that here you will be three inequalities. So when k equal to when we consider non-negative orthant as a cone here, that will be like, then you will have a set of linear inequalities. In that case, we can say that what will be that? Then we have affine function or linear function, linear inequality, and linear equality. That will be an LP. That's why it's saying linear programming. So where when we use k, the cone is r plus, then it's linear programming. But this is not just restricted to linear programming. You can use any cone here. When you use a r plus cone, then that's linear programming. But when you change the cone, that can mean many other things, not linear programming. LP is a special case of this. When you use a particular cone, yeah. So then it can extend from LP r plus to non-polyhedral cone. So what is non-polyhedral cone? So polyhedral cone will be of this shape. Okay, so which will be having a flat surface. Basically you are here you are having inequalities like this. Okay, so each inequality will be half space, right? So you have different half spaces, and if you have a cone associated with that, that will be having a flat faces. But you can of course come up with a different k where this is not flat, this is not polyhedral, so it will be having round shape or curved shape, something like this. So this is a polyhedral, non-polyhedral cone. So can you say an example of this? We just saw here, just few slides before we saw this. A second order cone is a non-polyhedral cone where it has this ice cream scoop kind of shape. Okay, so then so yeah, so let me conclude this slide and then we'll take a short break. So what we are seeing here is, this was our like without k, this was our original or the problem, the form of the problems that we discussed so far. Now what we do is we replace this inequality with a generalized inequality, okay, to get a generalized class. And now then, for this problem to be convex, the Fi has to be k convex, okay. And also remember, this inequality is defined with respect to a cone, which has to be a proper cone. And now this is the generalized inequality version of convex problem. Now what we are seeing is a special class of that. Within that, special class of problem which is called conic form of problem, where it is the same except from the fact that f0 and fi are affine function. Okay, so then what I'm saying is in this special class of problem, if you consider a cone here, and we are considering, if you consider r plus cone non-negative or thin, in that case this will be an LP, our normal, the very basic class what we were seeing before. Okay, so let's stop here for a small break. Now we will see what are the other cones, some of the interesting cones, and move forward. Okay. Okay, let's continue. Yeah, so we saw what is generalized inequality constraints, and how can we form a convex form using that, and we saw a special class conic form. Yeah, so you may revise this concept of generalized inequality. This is I copied from our last couple of lecture back. So you should be thorough with this. So there are at least the two famous generalized inequality where you use this cone and this cone. In this case, this will be component-wise inequality. In a PSD cone, we will say that x is greater than y when x minus y is PSD. Yeah, so let's move forward. Semi-definite programming. Yeah, so this is again a conic form. So we just saw what will be what is happening when you use this specific cone. Then you will get an LP. Now what we are going to see is the case where we use the cone of semi-definite. Uh, I mean positive semi-definite matrices. So that's the cone. So yeah, so this is a conic form problem where you use this special proper cone S and plus. Yeah, so how do we write this? Let's see what it is. So again, C transpose X minimize an affine function, and we have this uh, affine equality. There is no change, but here see what we had in the conic problem was this. We were defining an inequality with respect to cone K. Now what I'm saying is that this is a matrix. uh, I'm using this cone, particular cone, PST cone, which is used to compare matrices. So now what I'm saying is, instead of this, now what I have is something like a function of AX, which is a matrix. Okay, so whether that is less than or equal to 0 with respect to this specific cone. So now we have a function AX. Let's take an example. Here we have an AX. Okay, it's a specific example, x1 plus x2, x2 plus 1, x2 plus 1, x3. Okay, so in this example, one second. Yeah, one thing is, we'll see that. In this specific example, what we are saying is this matrix, as which is a function of x, is PSD, or in this case, it is negative semi-definite matrix. Okay, negative semi-definite. All the eigenvalues are 0. Okay, we may sometimes uh, do the discussion based on PSD, but both are like very similar. If this has to be, then I can bring a negative sign here and make this a PSD here, like this. Okay, so there is no issue. Yeah, so for example here, yeah, here we are considering a negative semi-definite matrix because our inequality was in this form. Okay, uh, right, so it is to, so we say that we are saying that a matrix is less than or equal to 0. That means negative semi-definite. Yeah, so my point is, if you have a matrix like this AX, and instead of writing this, I can come up with a different way. So what I do is I take x1 and multiply this with this matrix, x2 multiply with this matrix, and like this. So if you add all these things, all these guys together, you will get this. Okay. So this is a convenient way or common way of representing such inequality, where it is written like this: x1, that is first component x1, into a matrix f1, x2, f2, like that, plus a matrix G is less than or equal to 0. So yeah, so in this case, yeah, this is called, this sort of inequality is called linear matrix inequality. We already saw this in one of the previous lectures. Okay. So we are having several matrices, constant matrix, and multiplying with each components of the vector or variable and adding together, and we are saying that there is a constant matrix here also, and adding that, we are saying that that is less than or equal to 0, means that is negative semi-definite. Yeah, so a problem in this form is called semi-definite program, STP. Okay, so basically it's a conic program. Okay, nothing but a conic program where we use this particular cone. Okay, positive semi-definite cone. So this is a conic program where we say that we have a matrix which is a function, matrix contain which is function of our variable x, something like this, which is a negative semi-definite matrix. That's the thing. Yeah.
But
So yeah,
there we haven't mentioned like near to the inequalities and the K.
yeah. So here, so the thing is, we have, that's why what we have very famous two inequality we often used, which is R plus and S plus. Okay. In this case, we can do, if you see something like this, x, that you have a vector x less than or equal to vector y. By default, even if you don't specify this, okay, let this be like this. Yeah. Even if you don't specify this, it is understood that you have to, by default, this will be R plus, Rn plus. Okay. And if you have a matrix, right? So then by default, if nothing is said, that means this is with respect to Sn plus. Okay. Yeah. So here the cone is S, and you are comparing matrices here. G is a matrix and this guy together is a matrix. Since you are comparing matrix, you don't need to say this. Otherwise, it is understood that it is with respect to this cone. Yeah. So this is the form of standard, but this is a standard semi-definite program. But you may ask, like, why? Some you may ask, okay, so this is involving one set of f. So can you have a different? For example, you have one constraint here, x1 into involving f hat matrices f hat. Another constraint, a different set of matrix f tilde. Okay, but this also fit into this STP framework. We can easily rewrite this like this: x1 into all this. You create a matrix, block matrix with a diagonal. Block diagonals are these guys. Okay, like this. Now you are saying this is less than or equal to 0. This is possible because block diagonal matrix is PSD, positive semi-definite, if and only if the diagonal blocks are PSD. So when you write this, what you will be, so when you write this, what you will be getting this is this x1 f1 plus x2 f2 plus, right? You will have this, then 0 0, then the same guy with the x1 f tilde, right? You will have this. So now you are saying that this is negative semi-definite. Yeah. So you can say a block diagonal matrix is PSD when the blocks are PSD itself. Here I made the statement with respect to PSD, but in our case it is negative semi-definite matrix, but both are similar. You can make the same statement for negative semi-definite also. That means you are saying that this is less than or equal to 0. That means this high has to be less than or equal to 0, and this matrix also has to be less than or equal to 0. which is this two. Okay, so my point is, even if you have multiple LMI constraints, linear matrix inequality constraint, even if you have more than one of these, you can just combine that and write a single LMI using that. Yeah. So anyway, the important thing what here is about semi-definite programming, which says that this is a conic program where we use the specific cone, which is a positive semi-definite cone. Yeah, here I'm just showing a proof or just an example where the when can you say when this is PST or negative semi-definite, how can you say each up negative semi-definite? You can read this later. Yes.
So the only requirement for F is that it is symmetric. Is that correct?
Yeah. Yes. Yes.
Okay. Yeah.
Yeah. Yeah. I forgot to mention this. So this has to be symmetric. Yes. Now let's see. We see that this is this STP is the general class of all the problems that we saw so far. Anything LP, QP, QCQP, SOCP, everything. So let's see. Let's just take one as example. Yeah. So LP as STP. So you have this. This is the LP, right? Linear programming, where you have a affine function and affine inequality. Okay. So of course you can think about this other guy equality, but we are dropping this because that's not. You can add this and make the same discussion, but that's not focus here. Yeah. So this is the LP where yeah you have this inequality here, which is a component wise inequality. And now how can you make this fit this LP problem in an STP framework? So what I do is, okay, what is this? AX will be a vector, right? AX will be a vector. You are multiplying matrix with a vector, so that's a vector. So I take diag of AX minus B. Okay, so that means we take each component of this vector AX minus B. AX is a vector, AX minus B is also a vector. Take each component and make a big matrix where the diagonals are these components, and the other part of diagonal elements are zero. Okay, and now what happens if you say that this is less than or equal to zero with respect to here this inequality is with respect to which cone? No, you are comparing matrix, right? Yeah, so it has to be Sn plus. Okay, so what does this means? This means that this matrix has all its eigenvalues less than or equal to 0, right? That so this is happening for a diagonal matrix. This will happen only when the diagonal entries are less than or equal to 0. So that means you can say that this is less than 0, this is less than 0, this is less than 0. So what I'm saying is this is an STP problem where you are using a matrix inequality, but that is essentially what it is doing is an LP. Okay, so LP can be visualized as an LP.
LP can be visualized as
No, when you compare vectors, it is Rn plus. So
Like on the left there.
sorry.
Yeah, like on the left there, AX. And
Yeah.
B.
So
That's
here it is Rn plus 1. So this is not a rule. Okay, you should not say that. Okay, you can only compare vectors using Rn plus 1. Not a rule, but these are two common, very often used inequality. Even if you don't remember anything else, you should at least remember this. When you are comparing two vector, then the cone associated with that comparison is Rn plus. When you compare two matrix here now this is a matrix, then the cone is PST. Okay, so here it's a vector, so Rn plus. Here it is Sn plus. Yeah. So we saw how LP can be written as a STP problem. Now we'll see how SOCP is written as an LTP problem, STP problem. Yeah. So this is our SOCP, right? We have an affine function or linear function. Okay. One thing is, even if you put a constant here, just a general comment, not something related to SOCP. Let's say I'm putting a constant here, like q. Okay, q is a constant. Okay, there is no change. It will minimize for the same value of x because this is a constant, right? Q is a constant, so that will not affect the optimization part. So optimum point will be same. For example, if x star, let's take x star as the optimum point, so that will be same even if you add a constant here. But optimum value, to get the optimum value, you have to add this constant. That's it. Okay, so what I'm saying is, you find, if this was your problem, you find x star as the optimum value, the optimum point, and f star x is the optimum value. But for this new problem, the optimum value will be f star x plus q. Yes, so let's see how we can write this framework, rewrite that and see that, show that that is an STP problem. Yeah, so this is the SOCP, minimize F transpose X, subject to this. This is the second order cone condition. So one interesting thing is, before going into the detail, so here also this is a conic program, conic form problem. Why? Because this is minimizing F transpose X, subject to what is a conic form? What does this means? See, when you saw what was a cone, when you second order cone, sorry, was in this form, right? Xt such that this was the second order cone, the ice cream shaped cone. Okay, so that means xt belongs to the second order cone. Okay, yeah, yes, for second order that should be norm 2, otherwise it's a norm cone. There can be any norm cone. Yeah, so uh, yeah, so what here we have is something similar. Okay, so what we can say, that we can rewrite this SOCP problem as x, this is our t now, xt is less than or equal to 0. I have to put a minus here. So in other way, what I'm saying is, this is a constraint where you are saying that an affine function of x, okay, affine function of x belongs to uh, or an affine function of x is associated with a generalized inequality where the cone ki is the second order cone. Okay, so what I'm saying is, the SOCP itself is a SOCP is a conic form where you use a specific cone called second order cone. Okay, so this was not we were discussing. We were discussing how to visualize SOCP as an STP. Okay, for this we use uh, okay, we use a concept called Schur complement. Before that, let's just start from the final answer. So I will rewrite SOCP as an STP where same objective function, and in this constraint I rewrite as a matrix inequality like this. We'll see how this is equivalent. These are equivalent. We'll see how that is. For this, so now what we are saying is, this is a matrix, a symmetric matrix, right? These guys uh, are symmetric. Yeah, this is a symmetric matrix, and that is positive semi-definite. This is what we are saying. So how can we say this? So for that, you have to again revise this concept. We already saw this Schur complement. You have a matrix X in this form, A, B transpose C. So X is a symmetric matrix. In that case, uh, and yeah, A has to be symmetric. Okay, then this particular sure complement of A in X, sure complement A in X is defined as this C minus B transpose A inverse B. This is how it's defined. Okay, now we use this concept sure complement here. So any matrix X in this form P Q Q transpose R. Okay, so this is, remember, not the symmetry here. This is PSD. There is a theory. There is a result. X is PSD only if and only if P is PSD. That's the first condition. Second condition is sure complement of P in X is PSD. Okay. So what is first condition? That means P is greater than or equal to 0. P is a matrix. Okay. So that means what is our P here? This guy. So this is P. This is Q. Q transpose. Let me see. P Q Q transpose R. Okay. Yeah. So what I'm saying is this P is greater than or equal to 0. Okay. This is a matrix with a diagonal. What is this? I is a diagonal matrix, right? Identity matrix. So now its elements are given by this scalar. Okay. Now this will be PSD when these scalars are greater than or equal to 0. Okay. So that's the first condition. So yeah. So this is the first condition. Second condition is R minus sure complement of P in X, that is given by this formula. Okay. So that means in our case it is this guy R minus Q inverse Q transpose P inverse B. That has to be greater than or equal to 0. Just pick the value R Q B from our original matrix here. Okay. Then you can evaluate that and make simplification and get this guy. Remove the square from both sides, then you will get this. This is basically our SOCP inequality. Okay, so we prove that here, or we show that an LP and SOCP can be equivalently represented or can be fit into an STP framework. So now STP is the mother of all the problems that we saw here. Yeah, so let's now visualize whatever we studied so far. So first we have LP, QP, QC, QP, SOCP, then STP. Okay. Now everything comes under a framework called CON program. Okay. Also, maybe you can write something like so this is the whole field of convex optimization, where like CON program is a well studied area. So in this course, what we were focusing was on CON program. So whatever we discussed so far fits under CON program, specifically under this category, STP. Okay, so we can say that this was what we discussed so far in last 10 days or 7 days, this area. Okay, of course there is, we can come up with a CON program is a special class of generalized inequality program, where we were just using affine functions in the inequality. Okay, so I don't want to put that. This is a beautiful way of representing this. So this is clear. So yeah, one of the thing that we can write here is CON program. In CON programs, we were using any general CON K. In STP, we were using which CON? Sn plus, right? So in what else we saw? In SOCP, this was a particular CON called second order CON. In LP, this is R plus. The CON was R in plus. Okay, and any class here. We even saw that SOCP can be represented as an SPP. So then we already saw, so any of these subclass can be represented as SOCP. Okay, so everything is fitting into this hierarchical classification. Yes, so yeah, that's it. Yeah, so one more point, when you have a solver, I think you will be learning CVX soon, Friday, I guess. Yeah, so that is the solver is the architecture is defined for maybe this higher class STP. I think it's STP. So then it is solving an STP problem. Whatever you give, it's solving an STP problem. So even if you give an LP, it doesn't solve a specific, it doesn't have a specific solver for LP. It will solve LP as an STP problem. Yeah. Yes. Now let's see two examples of this and stop the today's lecture. One is eigenvalue minimization. So it's easy. It was not easy, but now for us now it is easy. So minimize. This is the function. Minimize uh, maximum value eigenvalue of AX. So you have a matrix AX given by this. Okay. Now what you are asked is to minimize the maximum value of this matrix. So this is not easy because how do you find the eigenvalue of a matrix? You have to take the characteristic equation and take the root of that, right? Equate that to consider the root of that. Then you will get the eigenvalues. Then pick the maximum value. So what happens if you have a like your polynomial, characteristic polynomial has a power like 100. What do? You cannot do anything. It's there is no direct formula to find that. So this problem itself is very complicated. You cannot solve this very easily. But now we can apply some tricks. What is the trick? So one thing is since it has a complicated function in the objective part, we will just use the epigraph form. This we already saw. How do you use the epigraph form to solve? Just replace this guy with a t, a symbol variable t, and then say that now we are minimizing t, and then say that this is less than or equal to t. You have something to minimize, okay? So remove that and put a t and minimize t. And the original quantity that you want to minimize is less than or equal to t in the constraint. This is the epigraph form. So according to that, what we can write is equivalently, we can write minimize t subject to lambda is less than or equal to t, right? Yeah. This is the epigraph form, okay? Epigraph is the regions which is above the function. That has nothing to do with this inequality, okay? This is the epigraph form of solving an optimization problem. Here, if you see why this is called epigraph form, this we already discussed in the 2 class back. So you have a function like this. Now you are saying that you have a function like this. Now you are saying that instead of minimizing in x, now let's consider two variable x and t. But so x and t is this guy, and minimize, reduce t, find a minimum value of t such that this function f of x is less than or equal to t. So this t, this inequality comes from here. This is the epigraph way of solving the problem. Okay. Yeah. So then what you are doing is you will be searching over this for a particular t. Then you will reduce t, and then finally you will reach this point. This is the way to solve this. Yeah. So I have this epigraph form, minimize t subject to this. And so how do we, again, this is also not simple, right? You have this guy lambda max here. So how to get rid of this? How do you do that? For that, yeah, we just, this is simple. Eigenvalue of A is, let's say eigenvalue of A is, a matrix A is lambda I. Then what will be the eigenvalue of A minus T into I?
Lambda minus.
So you are subtracting a unit matrix where the diagonals are just T, right? Unit matrix multiplied by a scalar T. So the new eigenvalue will be this. Okay, keep that in mind. Now, yeah, so here I am just showing a simple way uh, how it is happening here. You can read it later. Now, what I'm saying is that, so let's take this. A is less than TA. Okay, that means A minus TA is less than or equal to 0. That means all eigenvalues of this matrix is less than or equal to 0. Right? This is an inequality with respect to PSD cone. Okay. So this is negative, means it is saying that this matrix is negative semi-definite. That means all the eigenvalues are less than or equal to 0. Okay. So then, if all the eigenvalues are less than or equal to 0, that means uh, if you replace the eigenvalues of A with a maximum of this, that will also be satisfied, right?
Say it again.
So what I'm saying is, if the all eigenvalues are less than or equal to 0, so that means you have eigenvalues of -1 plus -1, -2, or -20, something like that. So that means the maximum of that is -1, will also be less than or equal to 0. So this is equivalent to this. Okay. So in other way, instead of saying this or instead of saying this, which was there in our epigraph form, I can just say that this will do. So now I take this and put it here. Okay. So now we rewrote this problem through an epigraph form to this way. Now this is an STP problem which can be solved easily. Okay. So this was not even possible if we don't know the STP framework and these techniques. Okay. Because this is very difficult problem. Now we can, this is a convex problem. We can solve this. So let's take this example and stop. So again, it is same guy, same problem, where we minimize matrix norm, minimize matrix norm. So what is a matrix norm? Norm of a matrix AX, A is defined as this. It is the maximum eigenvalue of A transpose A and root of this. Now, again, you are asked to revise eigenvalue decomposition, singular value decomposition. Okay, revise this. Fine. You should be knowing what is an eigenvalue and singular value. Yeah. So again, anyway, forget that. So let's consider this quantity function, which is norm of a matrix. It's defined as, you take the special matrix A transpose A, take the maximum eigenvalue of that, and take the square root of that. Okay, that is how this norm is defined in the context of a matrix. And yeah, so here A need not be a symmetric matrix. It's a general P cross Q matrix. That's why we didn't directly go for eigenvalue like this. Here we are constructing a new matrix A transpose A. Yeah. So what I'm saying is, yeah. So this is again an equivalent problem. We can minimize this using an STP framework. Where? So let's see how it is. It's same procedure. So this was our original problem. Now we bring the epigraph. Minimize t such that this norm is less than t. Okay. What is the norm? It is the maximum eigenvalue of this special matrix and take the square root of that is less than or equal to t. Equivalently, square both sides. You can say that this is less than or equal to t square. Okay. What does that mean? So you are saying that maximum eigenvalue is less than or equal to t square. So I can write that all the eigenvalues are less than or equal to t square. Or in other ways, following the similar argument, what we did here, I can say that the matrix A transpose A minus t square I is, this matrix is having eigenvalues less than or equal to 0, or that is a negative semi-definite matrix. Also, we know that uh, t has to be greater than or equal to 0, because this quantity, of course, would be greater than or equal to 0. Okay, because this is a eigenvalue of A transpose A. This will be positive. Okay, so because this is a PST matrix, you can revise your concept for PST, positive semi-definite matrix. Yeah. Anyway, the thing is here, this is greater than or equal to 0. Yeah. So then what I'm going to do is I am combining these two guys and writing this as Ti, constructing a bigger matrix and writing this. Why this is true? This is PST only if, again, our argument regarding the sugar complement. We'll bring that here. Even if you have some doubt, I'm going a little fast, but you can just connect, read that, and link it. Okay, there is nothing new. The same argument. There is no new concept. So this is PST. First case, Ti has to be greater than or equal to 0. That means all the eigenvalues of this matrix is greater than or equal to 0. That means T has to be greater than or equal to 0. Second is Ti minus this into this inverse into this has to be PST. Okay. So this you can, this is equivalent to this constant. So in other way, what here what we did is we found an equivalent way of writing this difficult problem, which is minimize t subject to, instead of this, now we can write this guy here. We can write like this. So this is a matrix inequality, which is an SPP framework. Okay, so let's stop here. We have 2-3 minutes. You can, if you have some doubt, you can ask.